Welcome folks to this video on vector calculus in which we discuss the dot product. So the dot product is our first vector product. We'll go ahead and see the definition, see some properties of the dot product, and then see a couple of applications. So here's the definition of the dot product. The dot product is defined as a way to multiply two vectors u and v. Given vectors u and v, the dot product of u and v is the sum of the products of the individual components. So u1 v1 plus u2 v2 plus u3 v3. Now, a quick observation here is that the output of the dot product is a scalar value, so just a number. Again, the input two vectors and the output is a number. So go ahead and check out an example. Here's an example. If u is 8, 1 minus 4 and v is 5, 2, negative 2, 1, find u dot v. Now here I'll go ahead and write this out in all of its gory details so that we see the details, and then in practice you'll probably get pretty quick at doing all this. So in this case we see the dot product is 8 times 5 plus 1 times negative 2 plus negative 4 times 1. So just crank out the numbers here and you end up with 34. So the dot product of u and v in this case is 34. Okay, let's go ahead and have a look at some properties of the dot product. Again, here's the definition of the dot product, and here are a few properties. The first of these properties is a commutative property. The second is a distributive property over vector addition. The third is a distributive property over scalar multiplication. And the fourth is the relationship with the magnitude of a vector. So the inner product, or the dot product of a vector with itself, is the magnitude of that vector squared. And the way that one derives all of these properties is by going back to the original definition of the dot product. So in this case, I've illustrated how to show the commutative property. Start with the definition that u dot v is u1 v1 plus u2 v2 plus u3 v3. Now, of course, because scalar multiplication itself is commutative, we can switch around the u's and the v's in this line, and we're left exactly with the definition of v dot u. So all of our different properties work out this way. Another property is the geometric interpretation of the dot product, which tells us that when u and v are non-zero and theta is the angle between the vectors, that the cosine of theta is related to the dot product and the magnitude of the vectors. And you can see this pretty quickly using the law of cosines, as it turns out. So here's the law of cosines expressed in terms of the vectors u, v, and u minus v, and of course the angle theta is the angle between u and v. So we derive this geometric interpretation of the dot product, expanding the magnitude of u minus v squared, the magnitude of u squared, and the magnitude of v squared in terms of their dot products. So using some of those distributive properties from the previous slide, we can show that the magnitude of u minus v squared, which can be written as the dot product of u minus v with itself, can eventually be expanded into the magnitude of u squared minus 2 u dot v plus the magnitude of v squared. And substituting that into this expression allows us to cancel a bunch of terms and eventually express the cosine of theta in terms of the dot product and the magnitude of u and v. So here's that expression with this sort of quadratic form for the inner product of u minus v with itself substituted in. You can see quickly that a bunch of terms cancel here, the magnitude of u squared, the magnitude of v squared, and we can solve algebraically for the cosine of theta, of course remembering that the only way that a magnitude is zero is if the vector itself is zero, so that when these vectors are non-zero, we can easily divide by 2 magnitude u, magnitude v to obtain an expression for the cosine of theta. Okay, so this is a really cool property that allows us to relate the dot product of two vectors with the angle between those vectors. And it turns out that this idea extends to higher dimensions, and it extends to things that you wouldn't even think of as vectors that you might get a chance to explore if you ever take the course in linear algebra. Super cool idea. In any case, for our purposes, this allows us to determine when vectors are orthogonal or perpendicular. So again, this geometric interpretation of the dot product tells us when the vectors are orthogonal. So we'll say that two vectors are orthogonal if the angle between them is 90 degrees, or when the theta between them, the theta from that dot product is pi over 2. Of course, cosine of pi over 2 tells us that the dot product is 0. So this condition that u dot v is equal to 0 is a way to tell us that vectors are perpendicular. So here's an example that illustrates that property. I'm going to write down two vectors here, u and v, where one of the components of v is unknown, and we'll solve for that component assuming that the vectors are orthogonal. Okay, so the way we do this is, again, with the geometric interpretation of the dot product. So here we see that the dot product of u and v is 18 minus c. Of course, if we want these vectors to be perpendicular, we need the dot product to be 0, so that tells us that c has to be 18. Okay, we'll go ahead and look here at actually a couple applications. So the first one involves a thought experiment, and the thought experiment is given two vectors u and v. Let's go ahead and think about trying to find a formula for the shadow of v that's in the direction of u. So I'll show you what I mean by that by a picture. Okay, so here's a vector u and here's a vector v, and I've drawn a magical mathematical sun and tried to stylize the shadow of v in the direction of u with this thicker line along u. Okay, so we'll use a couple things we know. Of course, if we take this angle between the vectors to be theta, then we can see that the shadow of v in the direction of u is related to the adjacent side and the hypotenuse of a triangle, so the cosine of theta. So for the time being, I'm just going to call that length of shadow little l, and of course it's the length of v, the magnitude of v, times the cosine of the angle between. Okay, so this looks a little bit like the geometric interpretation of the dot product. It's just missing a magnitude of u, which we can actually create by multiplying and dividing by an appropriate quantity. Okay, so here I've written this length L kind of in a funny way, multiplying and dividing by the magnitude of u. Not totally obvious why you'd want to do that right away, but if I write down the geometric interpretation of the dot product, then we can see that we can actually compute this length L just by knowing the dot product and not really needing to know the angle between them. Okay, so here is that dot product where I've just written L in terms of the dot product and the magnitude of u. So again, that's the length of the shadow. Now, of course, one of the things we talked about is creating a vector with a certain length. So if I wanted to do that, if I wanted to make this into a vector instead, the vector with the length of the shadow in the direction of u can be created by, again, just multiplying a unit vector in that direction by the desired length. Okay, so here again we see the length of that vector u dot v over magnitude of u, and if I want to create a vector, again, just multiply by a unit vector in the direction that you want. So here I've written that unit vector as u over its magnitude. Okay, so these two items are related to the projection. So the first is called the projection of v in the direction of u, and it's exactly that vector that we just found. So again, I've written that projection of v in the direction of u as u dot v over magnitude u times u over its magnitude, which we can express in terms of two dot products and the vector u. So again, here are the vectors u and v, and the notation here is, again, the projection of v in the direction of u. Okay, the other thing to be aware of here is the length of that vector, and of course the length of that vector is just u dot v over the magnitude u, and that's called the component of v in the direction of u. So again, the component of v in the direction of u, that's the length we found on the previous slide, and the projection of v in the direction of u is the associated vector. So when you see comp, that means a length, and when you see proj, that means a vector. Okay, so a quick example here. If u is 8, 1, negative 4, and v is 5, negative 2, 1, let's find the projection of v in the direction of u. So just a couple quick dot product computations. We see that u dot v is 34. We did that one before. And u dot u is 81. So again, the projection of v in the direction of u is that quantity 34/81 times the vector u, 8, 1, negative 4. Okay, super. Okay, here's another example. Let's go ahead and show that v minus the projection of v in the direction of u is orthogonal to u. Now, how do we show things are orthogonal? Well, we just show that their dot product is equal to 0. So in this case, we'll take the dot product of u with this vector given by v minus the projection of v in the direction of u. So here we've written u dotted with v minus the projection of v in the direction of u in terms of those dot products distributed over the difference of vectors using the distributive rules from before. And the first thing you see that happens is these dot products of u with itself cancel, and we're left with u dot v minus u dot v, which of course is exactly 0. Okay, super. So v minus its projection onto u is always orthogonal to u, and this has a pretty cool geometric interpretation if you go back to the picture that we had before and think about it. So if you go back and think about the picture we had before, of course, v minus its projection onto the direction of u gives us exactly the other leg in this right triangle, and what we're saying here is that this vector is always orthogonal to the vector u. This is actually a super cool idea that has tons of applications all throughout applied math. It's really important, for instance, in regression. Many of you have heard of regression, so this is the main idea behind that concept. Okay, one last application is the idea of work. The work is the component of the force that's parallel to a displacement times the magnitude of that displacement. So with a quick drawing, we can see that this is actually exactly a dot product. So if we assume that some object is moved from the first dot to the second dot, a displacement of vector d, using a force in the direction f, then the work is actually the component of the force in the direction of the displacement times the magnitude of the displacement. And we can see that this is exactly the dot product f dot d. So a quick example here. Suppose that we move a wagon 100 meters on a horizontal path by a constant force of 70 newtons, where the handle of the wagon is 35 degrees above the horizontal. So the work here is just a dot product of those two, which in this case, since we have the angle, we'll use that geometric interpretation here also. So in this case, we see that the work, of course, is the dot product f dot d, which is the force, the magnitude of the force times the magnitude of the displacement times cosine of the angle between. So 70 newtons times 100 meters times the cosine of the angle between, and just whip out your handy dandy calculator and you can find that that's 5734 joules. Now Newton meter is a joule. Okay. Thanks for attention to this video on the dot product. We'll see you next time.